So this is magnetic fields, and this is the difficult bits. The difficult bits. Now, some of these bits you won't think are hard, especially if you are one of those people that can visualize things in 3 dimensions without any trouble at all. And some of the people will think that this is really, really difficult, and they haven't got hope, because they find it really, really hard to visualize things. So, so I am going to pull up. Right. So this is the right-hand corkscrew rule. The only thing that's hard about this is remembering that it is the right hand, and also that your thumb has to point in the direction of, I mean, it says the current, but it's conventional current. We spend so much of our time thinking about what the electrons are doing. And of course, electrons are negative. And it's conventional current is the way a positive charge would move. So it's actually the charges themselves are going the other way, which is why this is difficult. Anything that makes things negative is horrible. It messes you up. So this is the right-hand corkscrew rule. Okay, I'm going to write it. Oops, I'm going to write it next to it. Oh, come on. Right-hand corkscrew rule. So what this is saying is that whenever you've got an electric current flowing in a wire, there is a magnetic field around the wire. In fact, and this is something that maybe I shouldn't say this because it might confuse one or two of you. If you find this confusing, then just forget I've said it. But actually, our dealings with electric circuits at A level, we think of as charges flowing down wires, and they do, but actually, really, what's happening is that you've got an electric field and a magnetic field traveling kind of around the wire. And this is why when your current changes direction, for example, the electrons in it are changing from one speed to another speed. They're accelerating or decelerating. And the consequence of that is they change energy level. And when they do that, they produce an electromagnetic wave, which we call a radio wave. And the faster you can make things vibrate, or you can get all sorts of different waves out. The truth is that electric currents are really kind of manifestations of an electric field and a magnetic field sort of curling around the wires and moving through space and persuading the charges in the wires to move. What we do when we talk about V equals IR and about potential difference driving charges around circuits is we're simplifying everything. We're saying that the connecting wires have zero resistance. We're saying that actually it's charges that are moving in the wires. And in fact, it's the truth is it's much more complicated than that. So what we're doing is we're kind of simplifying it so that we can do some sums, work things out and get stuff to work. So from the point of view of magnetic fields, though, you have to understand that there is a magnetic field around a wire if it is carrying a current. So you put your thumb in the direction of the current, and your fingers indicate the direction that the magnetic field is. The consequence of this right-hand corkscrew rule is that when you wrap that wire round and round and round and round into a thing we call a solenoid, you end up adding up all those little currents together, and you end up with a sort of a combination. I mean, it's a bit like superposition with waves. All of the little magnetic fields from all of the individual turns of the solenoid, they all add up, and you end up with a much, much bigger magnetic field, which looks like this one. Okay, I'm going to move that out of the way. So this is the magnetic field for a solenoid, right? And in fact, if you look at the ends of the solenoid, so if I was to put my eye here and look at the end of the solenoid, right, there you are, it's a bulging eye, then can you see that this one, the current is going anti-clockwise as you look at it from that end, so it's going this way anti-clockwise, okay? And you can tell that that is a North Pole because of this shape. I hope that you are getting this right. Can you see that the people who can think in 3D can kind of in their mind's eye look at that coil from that end, that right hand end, and you can see that it's going anti-clockwise. And if you've got an anti-clockwise rotation of the wires, the current's going anti-clockwise, then you get a North Pole. If, however, you look at it from the other end, okay, at the south end, then and you look at this this circle, can you see that the current is apparently going clockwise from here? So I'm going to make it go clockwise, and if your current is going clockwise, then you get a South Pole. Can you see how from drawing an N or an S you can determine whether it's a north or a south? That is what happens when you combine the different coils together. The magnetic fields kind of add up and you end up with a significant magnetic field. If you put a metal, an iron rod in the middle, then the magnetic permeability of iron, it's about 5,000 times more than air, which means that your solenoid suddenly becomes a proper magnet as opposed to being a meh magnet. And you can turn an electric current into a significant magnetic field. Yeah, this is because magnetic permeability is basically how easy it is for a magnetic field to penetrate that space. And this becomes important when you've got a coil, for example. I'm not going to say much about this because it's slightly off topic because this is electromagnetism, but I want you to recognize that when you've got a transformer with a primary coil, let's make it like that. Okay, so that's my V primary, and I've got a certain number of turns on there, and I'm going to change to a different color. Now, what's happening here is that my black square thing, that is an iron core. And what you end up doing with your iron core is you end up building what's called a magnetic circuit, actually. So you end up with a magnetic field, and obviously, well, I hope that you know that it doesn't matter. Let's make it go this way to start with, right? When you have an alternating current in a coil, what happens is you end up with an alternating magnetic field. And if you join it the way that this one is to the other coil, then you end up with an alternating magnetic field in the secondary coil, which induces an alternating EMF in the secondary coil, and you end up with an alternating voltage in the secondary coil. If you have a complete circuit, then that will be an alternating current. It will produce a current. So, and depending on the numbers of turns, you'll induce a bigger or smaller voltage. So what I want you to be aware of, though, is in the magnet there is a magnetic circuit. Do not think of it as a current, because it is not a current. Deliberately, the coils themselves are insulated electrically from the core. It is a magnetic circuit, and so the magnetic field builds because the primary voltage is building, And then as the primary voltage drops, then the magnetic field will drop. And as the primary voltage goes the other way, because remember, it only works if it's alternating, the magnetic field will build in the other direction. So you've got an increasing and a decreasing and an increasing and a decreasing magnetic field in that circuit. So you end up with an alternating magnetic field in the secondary circuit, which is why the BC thing works, even though there are no moving parts. So I want you to be aware that iron, the magnetic field will preferentially go in the iron. It's 5,000 times more magnetically permeable than free space or air, which is basically free space. So just to be aware that you get a magnetic circuit in, in a and I'm going to call it an iron core. Oh dear, that's really rubbish writing, Alison. Okay, right. So magnetic circuit in an iron core. Right, now I hope that so far I haven't done anything too hard. So not too difficult, maybe. I mean, electromagnetic induction, that transformer requires that. That's really hard, but not too much difficulty in terms of three-dimensional thinking yet. But now we're going to come on to Fleming's left-hand rule. So Fleming's left-hand rule is this F equals BIL thing. Okay, so this is one of the two equations for magnetic force. I mean, sometimes you put a B because it's the magnetic force. It's like you get a subscripted C for the centripetal force for circular motion. So the magnetic force is B times I times L. B is the magnetic field strength, which is nearly always called the magnetic flux density. So basically, it's how densely packed those magnetic field lines are, the blue ones. Those are magnetic field lines. The flux density is how closely packed they are. So you can see the flux density in the middle of the coil is constant, so it's a uniform field inside the middle of the coil. Here, the flux density isn't uniform because the flux density is getting less as you go further and further away from the wire, okay, for that one. So that's B, magnetic flux density or magnetic field strength. They are the same thing. I is the current and L is the length. So now these things, they all relate to one another, but they are all at right angles to each other. Okay, and the way that they're related is with Fleming's left-hand rule. So now I don't say the thumb as the thrust, as the motion. I say thumb as the thrust. So you could write thrust if you want. You can write motion if you want. You do have to remember which finger, sorry, left hand, which finger or thumb means what. So it's first finger field, second finger current, and thumb is the thrust. Okay, so I want you to remember which is which. It is your left hand. Okay, so your first finger's in the direction of the field, the second finger's in the direction of the current, and your thumb is in the direction of the force, the thrust. So that's the Fleming's left-hand rule, and that requires a certain amount of thinking about. The other problem with this is that they often combine it with Newton's third law, which just makes everything the other direction, and it's a pain. So I'm going to pull up, this is a Newton's third law pair diagram. And to show you how easy it is to get this wrong, I actually drew this wrong the first time I drew it. So please don't think that you're bad if you get this wrong. It's so easy to make a mistake. Right, now, I hope you can see the diagram has got one of these U-shaped yokes, and it's got these magnets, which are the flat ones, they're grey, and they've got the poles on the flat surfaces, the big flat surface. These are called Magneder magnets. Okay, so this is a Magneder magnets. And they're really nice because you can put them in on an iron yoke like that. And when you put them across from each other like that, you get a nice uniform feel between them. So you can make little electric motors and teach about electromagnetism and stuff. So they do appear in schools. Right now, if you put some Magnedur magnets in a yoke, a U-shaped yoke like that, on a set of scales, and then you pass a current through a wire that's going through that magnetic field, then Fleming's left-hand rule applies, and there will be a force on the wire. Now, I want you to do this with yourself. Now, please don't look at the picture of me if you've got the picture of me up, because my fingers are going to be pointing the wrong way compared to on your screen. And I can't just flip the image because then it would be my right hand and that won't work. So you've got to do it yourself, right? I want you to point your first finger in the field direction. That is the blue arrows. Your second finger is your current. So I want you to point your first finger to your right and the second finger to your chest. Point it at yourself. And you should see that your thumb is pointing upwards. So the force on the wire, actually it's the force on the charges in the wire, is upwards. And because it's upwards, the charges are effectively pulling the wire up. Okay, now I want you to be aware, and this is what I was saying about three-dimensionality and the fact that it's Newton's third law. Because there is an upwards magnetic force on the wire, there is an equivalent magnetic force on something else. Okay, remember Newton's third law. Some of you will remember how to write a description of Newton's third law really clearly. Okay, so when you write Newton's third law, I'm going to say that F is the force on the wire. F is a magnetic force. Okay, that's the type of the force, and it's the force from the magnetic field on the wire. Okay, and am I going to say that the magnetic field on the wire, on the charges in the wire? Yeah, something like that. Okay, so then there's a Newton's third law pair. Okay, so F prime, which will be the equal and opposite force of the same type on another object, is also a magnetic force, and this is the pink one. Okay, and it's from the wire, sort of, on the magnets. Yeah, magnets. Let's go from the magnets onto the wire and let's do it like that. That's probably simpler. Okay, so from the magnets onto the wire and from the wire onto the magnets. So there's a downward force on the yoke on the magnets thing, and there's an upward force on the wire, and they're equal and opposite, and they are in Newton's third law pair. The thing is, though, you see that there's an upward force on the wire, but a downward force on the magnets, which means that the mass apparently goes up, which is weird when you've got an upward force on the wire. Okay, and I want you to think how this works, because this flipping of things in 3 dimensions, this is difficult. Okay, it's very hard to get it right all the time, and nearly everybody makes mistakes. So that's Fleming's left-hand rule. Right, I just want to do one or two what seem like really ridiculous things. I want to tell you that the B field is a vector. Okay, direction matters. Most people forget, and they think it's just about size. And because most of the time things are at 90 degrees to each other, they don't think about it being a vector. But it is the perpendicular component of the B field that you need to worry about. Okay, so for example, let us imagine that we've got an aeroplane, okay, and it's flying this way, and it's going through a magnetic field which is at an angle, which it's bound to be if you think about it most of the time when you're not near the equator. It's going to be at an angle. So this is my magnetic field strength, right? If I wanted I've drawn an aeroplane, but how can I have a current in an aeroplane? Do you know what? I'm going to get rid of my aeroplane and I'm going to just put a wire in. But what I want to do is I want you to realize, let's have my wire, that they're not, I want you to realize that they are not at 90 degrees to each other, okay? I mean, in one respect they are. Dear, that's rubbish as well, isn't it? Oh, poo. Right, I'm going to make it really clear, okay? I'm going to make it so that they're not right. They're definitely not at right angles to each other, okay? So there is my current I, and my magnetic field is not at right angles to my current, okay? So that's what I'm going to do. I've changed my mind. So my magnetic field is not at right angles to my current, but it is only the component of the B field vector that is at right angles to the current that will give you the size of the force. So can you see that we would have to take components? Okay, so what I'm going to do is I'm going to take components of my B field. Okay, let's say this one. Right now, I need the component that is perpendicular to and parallel to my current. Okay, can you see that there, if I'm using that B field there, this is the perpendicular component and this is the parallel component. And let's suppose that that is the angle theta. Can you see that that bit there, that is also theta? And so it's going to be B sine theta. B sine theta is going to be the component of B perpendicular to I, okay? And so if B was, I don't know, let's go for 50 millitesla, and I is, I don't know, 2 amps, what would be the size of the force? This is the magnetic force. Well, it's BIL, but it's the component that is perpendicular to I that will give you the force. So you have to say, so it's F is equal to B and it's sine theta. That is the bit, that's the vector bit that is giving you the force, times I times L. So, I need to decide how long it is. How long is it? I don't know. Let's go for 2 meters. I don't know. Okay, so we're going to do 50 times 10 to the minus 3, because it's milli, times, how big's that angle? 60 degrees? Should we go with 60 degrees? So sine 60. So this angle theta is equal to 60, right? Times I is 2 times and L is 2. Can you see that this is how you, right? And there is no, I mean, it doesn't say on your data sheet that it's going to be B sine theta, but if they're not at right angles to each other, then you have to take the component of B that's at right angles, or you could take the component of I that's at right angles. It doesn't matter which, it works out to be the same. You've got to have the right angle bit, and it's very easy to forget that B is not a vector, because most of the questions, everything's all at right angles to each other, and they don't remind you often enough. So it's 50 times 10 to the minus 3 times sine 60 times 2 times 2, and I end up with only a very small force. I get F is equal to 0.17 newtons. Okay, So just so that you're aware, B is vector, right? Right, the next difficult bit that I want to have a word with you about is about circular paths. Okay, so charges moving in circles, okay, in a B field. Is that force acting down? Ooh. First finger's field. Second finger's current. Yes, it's going to be acting down. Yes, well done. Yes, it's going to be acting down. Who put another one? What does it mean if the mass on the scales goes down? It means that the force was upwards. No, the force was downwards. And then the force on the yoke is upwards. It's the other way round, Dylan. It's the other way round. Can you see how easy it is to get confused? Right, Dylan sent me a direct message, so most of you haven't seen it. What does it mean if the mass on the scales goes down? Oh, I'm sorry, I just didn't notice. Can you see that when the force on the wire is up, the force on the yoke is down, and the mass apparently goes up. But if the force was downwards on the wire, the equivalent Newton's third law pair force on the magnet yoke thing would be upwards, and apparently the mass would go down. So it's just the opposite direction. Right, okay, where were we? Right, so charges moving in circles in a B field. All right, first thing is, this is the condition for circular motion. You have a force that acts at right angles to the motion, okay? And that is the case in a magnetic field, Fleming's left-hand rule, right? Except that we're now dealing with a particular charge. So instead of not being able to go in that direction, because the wire doesn't extend any further in that direction, so it just pulls the whole wire up, the charges, the free charges, are able to go in little circles. So what happens is that's what happens. So if you've got a uniform field, and incidentally, crosses mean that the field is going down into the page. Sometimes, and it doesn't happen very often, and again, this is why you get confused when it does happen. If the field is coming out of the page, then they'll draw dots with little circles round. And the thing is, they do this so rarely that nobody knows that that's what it means. So they look at them and they go, well, which way's the field? How am I supposed to know? What do those little dots with circles around them mean? Okay, so here the field is out of the page. And here the field is into the page. And that's the only difference between them. The fact that the crosses are evenly spaced tells you that the field is uniform. Okay, and that's true for whether the field's into the page or out of the page, doesn't matter. Right, so I've got a nice uniform field. I've got a lovely, let's make it an electron because it's always harder with negative charges. First finger's field, that's into the page. Second finger is the direction that conventional current goes. So that's in the opposite direction to my electron. Pow! Do it yourself. And you should find that there's a force downwards. And what that does is it changes the direction. And then, can you see, as you change the direction, you're going to end up going in a circle. That's what happens. Oh dear, that's rubbish. Rubbish. All right, let's just stop there. I'm going to stop there. Okay, so it should be a complete circle. Right now, what I want you to know is that this equation always comes up. It comes up at least once a year, whether it's in a multiple choice question or whether it's in a longer answer question. You will have to equate that magnetic force, which is the BQV1, with the centripetal force, and it's nearly always, although not always, it's nearly always the mv squared over r1. That's the centripetal force, because it is the magnetic force that is providing the centripetal force. Okay, so if you just take that bit in the middle, you can cancel one of the v's and you end up with r is equal to mv over bq. Okay, And you can see that the radius of the circle depends on the mass of the particle, the velocity of the particle, the strength of the magnetic field, and the charge. All of those things affect the radius. Okay, I just want you to be aware that that derivation, you can see it's just 2 lines. It's really simple, but it will come up. Okay, and so that's one thing. But the thing that most people forget is that because the force is at right angles, okay, so because the force is at right angles to the direction of motion, and it's always at right angles to the direction of motion, kind of like by definition, because of Fleming's left-hand rule, right? It can't affect the speed. So it affects the direction, but it doesn't affect the speed, okay? Because it's always at right angles, it does not in large letters, underlined 4 times, affect the speed. So the speed of my particle is not going to be affected by the fact that it's going around in little circles, okay? And all it does is to change the velocity, and the velocity magnitude is not changing. It's just its direction. So, and that's something that lots of people forget. So, and this comes up occasionally when we've got what do you call them? Mass spectrometer. There we go. Couldn't think. So you've got a velocity selector which selects just one speed, and I'm going to do that in a minute. And what happens is that the particular speed of particle enters a magnetic field, and it bends it round, and it's kind of like, well, what speed does it come out at? And you go like, how am I supposed to know that? And then you realise, oh, the magnetic field just makes it go around in circles. It doesn't affect the speed. So whatever velocity it had when it went in, which you can nearly always work out from E times V, with the charge falling down electric voltage, is equal to a half mv squared. So you can work out the speed. Yay! So just so that you're aware, that comes up quite a lot. Right, so that's that one. I do want to talk about the velocity selector. Yeah, I'm going to stop at this point because I've pulled up the velocity selector as a question. Has anybody got any questions about what I've done so far? Because if you have, now would be a good time to speak. Otherwise, what I'd like to do is to look at this question. So you can see here, this is a velocity selector. Okay, so this question, I'm going to go back to the beginning, is about, it starts just there, it's about a mass spectrometer. So it says, read the passage and answer the questions. So a mass spectrometer is an instrument for measuring the masses of different isotopes. It's not just that, but that's really good. The main working parts of the instrument are shown in figure 1. So this is like a flow chart. So you've got a sample of gas. It's ionized. It's accelerated. Only certain speed particles are selected. The other ones end up spiraling up or down out of the way. And then it goes into the thing called the mass separator, where the different masses are made to go through semicircles, and depending on how massive they are, the semicircles are either bigger or smaller according to that R is mv over bq equation. Okay, so that is the kind of flow chart for a mass spectrometer. Right, so then it says figure 2 shows the components in more detail. So you've got the gas going in, it's ionized, you accelerate it using a lovely large voltage, VA, A meaning acceleration voltage. And then the beam of ions, and they're positively charged ions because you've accelerated them with a negative voltage. So that comes out. And then it goes into this bit, which is called the velocity selector. And then it moves, the beam moves into the mass separator, where it gets to go through semicircles with a magnetic field, which is what we were just talking about. Okay, so the velocity selector contains a region where there is a, look at this, uniform magnetic field at right angles to an electric field. Okay, so now what's drawn on there is the electric field. So you've got a positive voltage at the top and a 0 volts at the bottom. So you've got that potential difference between those two parallel plates. And obviously these particles, they're positively charged ions, so they are going to be attracted downwards. So the shape that they would make is not a circle, it's a parabola, just like you'd have a ball would fall down in a uniform magnetic gravitational field. A positive particle in an electric field will feel a force downwards. It's a uniform field, so the force is constant, so it will follow a parabola, just like a ball falling down. But in addition, it tells you that there's a uniform magnetic field that's at right angles to it, and the magnetic field is into the page. Okay, now I want you to be aware that they haven't drawn on here the magnetic field. And the magnetic field for the velocity selector is different to the magnetic field in the mass separator. Okay, just want you to be really clear about that. Okay, so the ions of different masses are separated by a uniform magnetic field, and that's what we're going to talk about, the velocity selector bit. So it asks you what's meant by ionization, and then it asks you to discuss the energy transfers, but we're going to do part C, which is this velocity selector. So this is a close-up diagram of the velocity selector. And there is a magnetic field which is affecting this beam of positively charged ions as well. Okay, so it says, discuss how the path changes when an ion enters the velocity selector with a velocity greater than v. So what we've got to do is we've got to think about what's going on in order to get a particle to go in a straight line. Okay, I have just told you that a particle here is going to feel a force downwards. A positive particle will feel a force downwards. Okay, and the force it's going to feel is absolutely equivalent to the weight equation. Okay, so in a gravitational field, a weight, a mass feels a gravitational force that is proportional to the gravitational field strength, G, multiplied by the thing that is affected by gravity, which is a mass. An electric force is going to be felt by a charge, Q, multiplied by the electric field strength, which is E. Okay, so there's an electric field. Now remember, I'm going to change color. The electric field is the way a positive charge would feel a force. If your lines are evenly spaced, it's a uniform field. So there is my nice uniform field. And we're told that it has an electric field strength of E, which means that my little blobby thing in the middle here is going to be feeling a force this way, okay? This way. That is the electric field, and it's QE, okay? That little e is a subscripted e, meaning it's the electric force. Right, now, in order for the particle to go in a straight line, there has to be another force that completely counteracts the electric force. Okay, I want you to be aware that the other force comes from the magnetic field. So it's first finger field, second finger current, and the thumb is the thrust. So I want you to realize that the field is into the page. So put your first finger into the page. The second finger is the current, and these are positive ions, so it's the way they're moving, so that's to the right. And you see that there would be a magnetic force upwards. So what I want you to realize is that if I'm going to draw a circle around this and draw a cross, which indicates there's a magnetic field into the page at that point, okay? And so we will end up with a magnetic force upwards, and it's exactly the same size as the electric force downwards. And I'm going to call it F subscript B, B for magnet Yeah, because magnet begins with a B, doesn't it? It's a B magnetic field. Okay, so FB is equal to, and now remember, this is not a charge in a wire, this is a charge free flowing, so it's a BQV one. So it's BQV, and that's the velocity bit. Okay, right now we can equate those two forces for the particles that go straight through. If they're going too fast, then B will be bigger and it will end up flying off upwards. If they're going too slow, then B will be smaller and it will end up flying off downwards. So the particles that are going too fast will end up doing this. So this is the too fast ones. And the particles that are going too slow, let's go with orange, they would do this. These are the too slow ones. Okay, because the speed, can you see it doesn't affect the electric force? There is no velocity bit in the electric force. So now we can equate those two. So we can say that QE is equal to BQV. Oh, look, it doesn't even depend on the charge. Oh, so our velocity depends entirely on the ratio of the electric field strength compared to the magnetic field strength. And obviously it's easy to change the electric field strength. After all, the electric field strength is just V over D. The D is the distance between the plates. It's very easy to change voltage. The magnetic field strength, well, that's a little bit more difficult to control. But if you've got some Helmholtz coils and you're doing it with an electric current, it's not that hard. So once you've controlled your E field and your B field, you can select any velocity you like, which is why it's called a velocity selector, because you can select whatever velocity you want. Okay, and there was only one more thing I wanted to go through, and that was the Hall effect, but it's not actually in any of the specifications, I don't think. So I'm really conscious that we've only got 15 minutes left. Right, has anybody got any questions about this? I hope you haven't. I hope I've explained it clearly enough. Because at this point then, what I'd like to do is I'd like to go to the question that was coming up on that paper, because I'd like to go over that, and we've not got all that long. Oh, pants, where was it? There it is. There it is. Knew I'd got it. Right. So this question came up on, I think it was the 2020 paper 3A for the AQA. So this is a practical paper, and it combined various different principles. Here there's a ruler, it's pivoted at that end by the clamp stand, and it's placed down gently on, it's actually a prism, which is on a scale balance. So you can see the force, but it's kind of like in terms of mass. So you have to multiply it by G, and where you have to convert it to kilograms first. You've got to multiply it by G in order to get the size of the force. So really what the scale balance is doing is it's measuring the size of the reaction force that's happening there. It's equal to this mass, but in kilograms times G. That's a force upwards on the ruler there. There's a force downwards on the ruler, which is going to happen, and we're told that the ruler, well, we're not. You have to assume that the ruler is uniform, and that was what they were expecting you to put there. But that's W is, well, this is a different mass. This is M, I'm going to put R for ruler, G, whereas this is MB for balance. It's the balance mass, the one that's read off the screen. And then this is the pivot point, P. Now, there is another force at P. There has to be, because this object is in equilibrium, and these two forces are not lined up, which means that that object would have a resultant moment. So there has absolutely got to be a force at P. It's probably downwards. It almost certainly is. But we've no idea what size it is, which means that we have to take moments about P. Okay, what's this got to do with magnetic fields, I hear you say? Nothing. But what I'm trying to point out is that they're combining moments with magnetic fields, because later on, doobie-doo, they put a wire along the ruler. And that bit of the wire, the bit that they've shaded grey, they put a magnetic field on that bit. So they have a North Pole on one side and a South Pole on the other. And that, if they've got a current going through that wire, which they do, then there's going to be a force on the wire. Okay, and so and here is the apparent balance reading. I mean, it's measured in grams, but it's not, I mean, it's sort of a measure of the force. You have to multiply it by G to get it as a force, and the current through the wire. And you can see it's quite a beefy current. That's so that you can get at least a reasonable change in the force, which will put a turning force on this thing. And they say that it can be shown right now. That's part C. We'll come to that in a minute. This says state and explain the direction of the horizontal uniform magnetic field. Okay, so right, first things first, we've got to realize that this is the positive and this is the negative of the battery, which means that the current flows from P to Q, okay? Which means that the current in this bit is going this way. This is conventional current, okay? And the other thing that I kind of brushed over is you can see that it says 214 here. And this is 238. Does it say? Right, as the current goes up, can you see that the apparent mass is going down? If the apparent mass is going down, Dylan, what direction is the force on the wire? The current goes up. The apparent mass goes down. What is the force on the wire? Okay, so in order for the mass to go down, the force on the scale balance has to be getting less. Okay, so that's the downward force is getting less, which means that there's an upward force equivalent there. But so this wire must have an upward force on it. Can you see? I hope you can see that. Oh, I got a chat. I didn't have the chat up. So, okay, so if the apparent mass on the scale is going down, there must be an upward force on the wire. Can you see that? In this situation, the yoke with the magnets on is not on the balance, remember. I hope you can see that. It's slightly different to the previous situation. So here, if there's a force up on the wire, that's going. So Newton's third law only applies when there's a yoke. It's not when there's a yoke, it's when the thing that's feeling the other force, right? On that diagram, the one with the yoke, that diagram, the wire was in midair. It wasn't touching the balance at all. So an upward force on the wire provides an equal and opposite force on something else, which happens to be the magnets and the yoke. So it's not got to do with the fact that there's a yoke. It's got to do with the fact that the magnets were on the balance. Here, an upward force on the wire is going to try and lift that ruler at that end. Can you see? It's going to lift this. And if this end goes up, even only slightly, can you see that this reading is going to go down? So here we're not dealing with Newton's third law because right, if you were looking, right, if you had your yoke here, can you see like that? So you've got your magnets. Oh, that's a really rubbish drawing. Right, let's try that again. Get rid of all of that. If I had my yoke here, like that, and let's do my magnetic field. So my magnetic field is kind of into the page there. Can you see that there's going to be an upward force on the wire, which I'm going to put in green, and there's going to be a downward force on the yoke, which I'm going to put in red. And those two forces are equal and opposite. Those are Newton's third law pair. But can you see that the downward force on the yoke is nowhere near the balance? It's not going to affect the balance. It's the upward force on the wire, which is attached to the ruler. It's going to lift that ruler just a little bit and make the apparent force on that prism, that balance, go down. Can you see that? I hope you can see that. So it's not got to do with the fact that it's a yoke. It's got to do with the fact that the Newton's third law pair force is on something that isn't going to affect the balance. Aha! Okay, good. Right. So Dylan has said that he understands it. Yay! Okay, cool. I'm going to clear my drawings. Right, so that was that one, which lots of, well, not lots, most people were able to do it, but one or two people just got completely tied in knots with that bit. This next bit is about this sigma thing. It's the change in force acting on the prism per unit current in the wire. And what you got from the gradient of the graph was the mass. And you have to multiply it by G in order to get the force. Yeah, it's horrible. It's a mean question, and there's so many pages of it, and it just goes on and on and on and on. But anyway, I hope that has helped. Again, right, this is much more like, Dylan, this one is much more like that with the yoke on the scales. Can you see that we've got a wire that is not touching anything? And we've got a wire that is now sitting on the scales. And what they wanted you to do was to wire these up so that they were wired in series. And so you had to do this, and then this ended up having to go over here so that the wire was going, the current was going the same direction in both wires. Can you see it's going that way and it's going that way? So they're going in the same direction. Now remember that a wire has got a magnetic field around it, but it's the right-hand corkscrew rule, which means that that's always to the right. So the top one has got a field that's going like that. Oh, that's very small. And the bottom one's got a field that's going like that. And so the top one is going into the page where the bottom one is, and the bottom one, the magnetic field's coming out of the page where the top one is. So if we just look at the top wire, okay, so the bottom wire has got a field coming out. So for the top wire, the magnetic field is out of the page. So first finger's field is towards you. You've got to make it go towards you. Second finger's current's got to go to the right. So the top wire is going to feel a force downwards. And the bottom wire is going to feel an equal and opposite force upwards. Okay, which means that the current, the apparent mass is going to go down. So again, this is Newton's third law problem, and that's how you do the direction on those. I hope I haven't confused anybody. But with this particular example, you needed to wire them up in series with one another so that you could be sure the size of the current was the same in both wires. If you put them in parallel with one another, in theory, yeah, it should still work. But I wanted you to be sure of getting them the current to be the same, and the only way you can be really sure is if they're in series, and then the current has to be the same because there's no alternative path. So lots of people wired this up wrong because they wired it up in parallel, not in series. So that was quite hard. Okay, I hope that we've been through enough of the difficult bits of magnetic fields that you are now, all of you, really, really clever and are able to do it all. And I will see you soon.